Welcome everybody. We are Maria Pociello and me, Ferran Batllori, and today we're going to talk about an invention that revolutionized the field of telecommunications. That is the telegraph. First, we're going to talk about its history and the relevance of this device. Next, we're going to see how a telegraph works and what are the theoretical concepts behind it. After that, we're going to see the results we obtained when making it. And finally, we're going to share our conclusions of the experiment. First, let's talk about its history. The telegraph was invented and developed during the first third of the 19th century. However, other discoveries and inventions were essential for its development, such as the discovery of the voltaic pile by Alessandro Volta, the theory of electromagnetism by Ampere, or the invention of the electromagnet by William Sturgeon and the improvement of it by Joseph Henry. But who invented the telegraph? Well, it's not clear who was the father of the telegraph, since the final invent was a succession of many discoveries and prototypes developed by different scientists. Many scientists did their own version of it, such as Ampere, Gauss, Weber, or Henry. But the most popular one, and the one who patented it, was the model of Samuel Morse, invented in 1833. Morse was famous not only for the invention of the device, but also for the well-known Morse code, an easy system of writing messages with just dots and lines. The famous first message that was sent was, "What hath got growth?" It means, "What has got done?" And during this presentation, we're going to replicate it with our own prototype. This invention supposed a revolution for the telecommunication field, since being able to send information at a great speed and long distances supposed a huge save in money and time. It was really used in sectors such as commerce, during wars, and many other fields. Soon, the telegraph became a very popular device and it was being used throughout the United States and Europe. Some decades later, the telegraph network reached nearly all the world, being the main tool used for communications. The telegraph system can be split into two parts, the transmitter and the receiver. Together, these two elements form a closed electric circuit, and when we push the lever of the transmitter, the circuit closes and the current starts flowing through the cable.
When the lever is pushed down as shown in the black area, the two conductors touch, closing the circuit and allowing the electrons to flow. As the intensity flows from minus to the plus terminal, the electrons will go the other way.
The current flows from the cable to the receiver, and it passes through the coil, balancing down the lever.
Ferromagnets are a type of metal, such as iron, that are formed by magnetic domains. Those are like tiny magnets that are all organized by chance, cancelling each other out. But when an external magnetic field is applied, the magnetic domains are oriented parallel to the magnetic field, creating a much bigger magnetic field as a result. This momentary intensity will generate a magnetic field. We know that it will be pointing upwards thanks to the right-hand rule.
As we have explained in the theoretical part, when a certain metal, as iron, is under a magnetic field, this one tends to be a magnet itself. That is why we'll find the wire around a metal tube, or in our case, a straw, because this will generate a much more bigger magnetic field as a consequence. In that sense, we can assume a north and a south pole to the magnetic core, such as the one in the figure. As a consequence, the tiny metal that is in the lever will suffer the same effect, and a north-south pole can also be assumed. This will mean that the tiny metal, as his south pole will be pointing down, will be attracted to the north pole of the magnetic core. Therefore, the piece of metal located on the lever will be attracted and it will balance down. This will cause the characteristic sound of the telegraph, a click. Otherwise, when the transmitter stops pushing the lever, the circuit will break and the lever of the receptor will go back to the original position thanks to the string.
Here we can see the inside of the box and the full circuit. From the jack connector arrives the current of the cable, passes through the coils, which are connected in series, and reaches the south pole of the battery. From the other pole, a cable connects the other pole of the jack connector, passing through a switch, and that closes the full circuit.
Here are the changes we did on the device in the process as to the correct functioning of it. We changed the copper wire to 0.8 instead of a 0.5 mm. We changed from a stainless steel screw to iron screws, referring to the coils of wire. We also changed from a 4 mm iron screw to a 12 mm. We changed a string for a smaller K. We greased the attachment points, and we changed the battery for a new one. The conclusions we arrived were: firstly, that a stainless steel is not a ferromagnet material. Then, the thicker the wire, the smaller is the resistance and the higher the intensity, by Ohm's law, and in consequence, the larger the resulting magnetic field. We also concluded that the bigger the diameter of the screw, the larger the created magnetic field, and that strings and friction must be taken into account.
With the evolution of science and technology, the telegraph started falling into disuse in front of the invention of the telephone or internet and electronic mailing. The last telegraphic companies in the world closed in 2006 in America and 2013 in India. Nowadays, there are some lines open for telegraph enthusiasts.